So today's session is going to have some more details about how IoT is implemented. I'm not going into the details of the processor which is being used, but at the very high level, why do we need IoT and why do we need AI in IoT? Then let us briefly look at AI running on cloud and AI running on the edges. Okay, so that's going to be the focus of today's class. I will introduce you to some electronics part of IoT, very high level. Maybe in the next class, I want to spend more time on the NVIDIA solution, particularly not architecture, but at least at the high level, so that you understand where the software that we write for IoT runs as far as the devices are concerned. I'm not talking about the cloud, but device side, okay, on the edge side. Okay, now you might have heard about firmware, software, hardware, then middleware is another one. Let us see what it is as far as IoT is concerned. Let us read this long sentence. In such a highly distributed, you know that IoT devices are all around the place and decentralized. See, the devices are expected to be smart to the maximum possible extent, and they are all not controlled in one place. Okay, it's like an internet. You know that nobody is having a control on internet as such. It is like the people are contributing to the flow of traffic on the internet, but no, there are some centralized control for allocating IP addresses and domains. All those things are there in internet. I'm not saying it is completely uncontrolled, but when I say decentralized, there is no one point of control for a internet. There is nothing like if that fails, the internet goes, whole internet goes down. It's not that way. So even if a country huge as US or very IT centric, even if internet is down in US, the rest of the world can still have a connectivity with the internet. So nothing like one country or one region is controlling it. So that's what is called decentralized. IoT is like that, like internet. It's a decentralized environment where even one device fails or one server fails in any of the IoT environment, still the things will work, the communication will happen. The reason being, we want this to be reliable, and we know that the IoT devices are working in an unreliable environment where failures are common, power failures are common, and even then the whole thing should not fail. So that's the reason behind we keep IoT in the decentralized way of managing it. Okay. So when we have that kind of environment, because it is a need for it, we need to have it as a decentralized. Because of that, we need a middleware standards and solutions also. Okay, for integrating those highly distributed decentralized environments as well as devices. So these solutions become handy in seamlessly and spontaneously integrating all kinds of sensors, actuators and instruments, appliances like fridge or TV, machines, maybe in the industry environment, equipment, even utensils. Sometimes even utensils will talk to the through internet, and there are various tools, so on. So we need, these are the things which are there in a decentralized environment and distributed. So we need some middleware which can make these things work together cohesively and reliably as far as possible. And they also connect to remotely held software applications. As I mentioned in the last class, it's maybe in the cloud. So that is the reason we need a middleware which manages all this. Now what does they do? What does the middleware do? Further, with the number of data sources, see, once IoT devices are more, they are going to produce continuously data. So their very huge data is coming from IoT, which is rapidly growing, and we keep adding more IoT devices into the system. So it's going to be exponentially increasing. We need to have a highly synchronized and integrated platforms for the design of such systems, development, debugging them, and deploying them, delivering the services to the customers, and also decommissioning. Suppose when these devices go, they live through the life, they die, the devices die themselves. We need to have a proper way of decommissioning them also. Decommissioning, starting is commissioning is starting, decommissioning is uh, kind of having a slow way of destroying them, okay, in terms of shutting down or whatever. So IoT data originating from sensors and actuators, you may wonder actuators or output, need not be always, because based on the action taken by the actuators, there will be some encoders. See, suppose if you are controlling remotely a robot hand to pick an item, this is actuator which is controlling the robotic hand to pick an item, but it has to give input also, what is the position of this hand with respect to the object continuously. There will be sensors like optical encoders or positional sensors or camera to continuously feed it the information about the position of these actuators, or the motor which is controlling it is also reading out some value so that we can control it efficiently. So the data generated by actuators also contributing to the IoT data. So they are gathered, cleansed, because you have to remove the noise and then extract the useful information. We have to process it. We should be in a position to query them, analyze them, and data mining is required to retrieve important beneficial knowledge from the huge amount of data coming from IoT devices. So they all need to be given to IT or business entities to take appropriate decisions. So it's like if the smoke sensors in a factory, all of them give an alarm, then it has to be sense that there is a fire hazard and we need to immediately raise an alarm to fire engine, fire services, and shut down the power to the industry factory. Those things have to be taken. So the high level decisions have to be taken based on the input from IoT devices. So that's about why we need middleware. Middleware is something which manages all the IoT devices because they are huge in number, and it helps in extracting the information, as well as it helps in building such a system, design it, develop it, and deploy it, maintain it, and even decommission it. So the middleware is kind of a platform or a software as well as hardware which manages all this. Now, why do we need AI in IoT? Okay, why we could have been just IoT course, but why are we learning as AI for IoT? I have already explained the reason partly. So let us see what is AI all about and deep learning. I am sure you might have seen this many times. You have a lot of courses already you are done. So as a continuity, I am just saying that AI is the first initially AI ideas came up 1950s. How to make a computer to behave like a human. Turing test is one example of testing whether a computer is intelligent or not like a human being. Then using the techniques of AI, all the search techniques and algorithms, we are implementing the machine learning. In this case, the machines are learning from data. We normally, in a normal programming, we just give the instructions to the machine to do what it is supposed to do. Whereas in this case, the data which is given to the machine is interpreted by the machine to learn about what it is supposed to do, and it programs itself. So a neural network is one such things where it extracts the information from the data fed to it. So learning happens. It is done by the machine itself, by themselves. So that is machine learning. And deep learning is something which much more kind of neural networks with multi layers, which you are also learning right now. So these are the ways the technology has grown. And the reason why AI, though it started off in 1950s, it was in dormant state till 2000. Okay, why was it in dormant state, and why are we talking about AI so much? And during my college days, it was not there at all. And when I did my MTech in 1997, somewhere here, AI course was there. Okay, but IoT and AI, it was not even thought of. Now we have both AI and IoT being taught together. So why are we doing it? The reason being, The AI algorithms or techniques are all power hungry. Though people thought about it, how to mimic the brain, they know that brain has billions of neurons, and if they need to mimic neurons in a machine, we need a very highly powerful machines to achieve that. It was not possible, though thought was there, idea was there, but it was not possible to implement them and see it working. So it was in the very thought process level only, but could not be implemented in real life. But why are we doing now? We have a huge exponential improvement in computing, especially in the chip industry, IC, integrated circuits. The semiconductor world has really contributed a lot for the growth of computing, especially in terms of AI and data science and internet or whatever. Without integrated circuits, we will be nowhere. So this IC industry, integrated circuit semiconductor industry, has made it possible now that we can mimic brain at a by the machines with the consuming not too much power and not consuming too much of space and energy. We can still achieve that kind of a speed and processing power. So that is why it is being talked about in the recent time, okay, in the last 10 years or so. Now, why do we need AI in IoT? Artificial intelligence is required and useful for making sense of the voluminous data generated by billions of IoT devices. Each device itself is generating more data, and we have billions of IoT devices now, and all of them need to work together. You can imagine the amount of data that needs to be processed to get a meaningful information. So AI is a must. Whether AI is going to be running on cloud or is it going to be running on edges is what is being debated and being worked on. But AI has to be there because we cannot make sense of data generated by IoT devices by humanly impossible to do it manually or using computing systems. More powerful computing system is required, and AI is required to make sense of the data. AI enables machine learning solutions that automate data analysis. As I mentioned, AI IoT devices are supposed to work on their own, not manually controlled, like what we do in terms of computers or whatever. So the data analysis we need to do in real life, in real time, and to get new insights into the data from the data, which was impossible to imagine by manual processing of data with the traditional methods or previous computing that solutions we had. So right now it is possible. If AI is the new electricity, okay, it's an analogy. You know that electricity was the earlier invention, and electricity was, okay, let me call electricity as pulses. It was, thermal energy, thermal uh, electric generation, thermal energy. So coal was used to generate electricity, and coal mine was feeding the coal for the electricity, right? So coal mines, we took coal from there and then we generated electricity. Now similar to that, IoT is coal mine now for us, and the data what it generates is the coal, and the new electricity is like a AI. So you can see that AI cannot exist without data. That's why Facebook and WhatsApp are fighting for data, because they want to run AI algorithms. The important thing is input has to be given. That input is huge data. Then only the AI algorithms can have a prediction which is closer to reality. For that, we need huge data. And who can generate huge data? People like China and India users can do it for FBs and WhatsApp. Whereas for industrial applications and home appliances, what we have, where we are trying to get AI into the field, we need the AI to be trained. For that, we need data. For getting the data, we need IoT. So IoT is feeding us. Actually, I can say AI survives because of IoT. Okay, so that's how it can be compared. IoT generates an enormous amount of data, we are currently processing only 10% of the data which is getting generated. You can imagine how much we are losing out. And The data is also not the lifetime of the data is not huge. It's milliseconds, so it's dynamic data. We need to be adaptive to the time dependent data which is getting generated by IoT devices. So manually monitoring them is impossible, expensive. It's not possible, rather. So this necessitates a way to intelligently analyze, okay, gain insight from this data, and using tools and models of AI, they provide us the way to do exactly with minimum human intervention. So now you understand why we need AI in IoT, and AI also needs IoT. Okay, it's like married. Both of them need their presence, because IoT cannot exist without AI. AI cannot exist without IoT. So they need each other. By observing the behavior of multiple things, IoT aims to gain insight into the data and optimize underlying processes. Okay, when I say IoT here, IoT system. Okay, so which includes not only the IoT end devices, it includes the AI algorithm running on IoT systems. Now, what are the challenges we have here? Storing real-time generated events, because IoT devices are generating continuously data or events, and we need to run analytical queries on them over the stored events. Somehow, if you happen to store them, you have to query them to get a meaningful information from there. Performing analytics using any of these techniques over the data to gain insights and make predictions. So AI learns from it and tries to predict what could happen in the future. So I hope this gives you an idea why we are even having this course. Okay. Now let us see what is fog or edge computing. Um, they are not same; they are different. Let me explain. I am sure you have heard about these names. Okay, actually, I mentioned a reference also. Please read that document, which is very well explained, nicely written. See, these are the IoT devices, okay, whatever sensors or whatever. There are some, the software running on the IoT devices are called as application here. Don't confuse with the application layer that I mentioned. Even the IoT devices have an application layer there, because see, it's like, let me explain with the OSI layer analogy. Okay, yesterday we talked about reference model of IoT. Okay, see, there are different layers in OSI, different layers in IoT also. Now let me talk about only this OSI layer, network layer. Suppose we have a machine with a running, which is also a OSI layer. Now imagine your laptop is there, and maybe your Google search engine, maybe Google server is here. Both of them are running the entire OSI stack. Okay, because imagine a Chrome application. Maybe I assume that Chrome is email or Gmail. Okay, let me take Gmail as an example. Gmail is running on some Google server here. We are having clients running the Gmail clients, which are running on all our laptops. There is a communication at the application level, and there is a communication between these two at the session layer. There is a communication at the TCP layer and IP. Everything there is a equivalent part of that in the both the places, laptop as well as in the Google server. So that's why I'm saying application could exist in the IoT device also, as well as application is here also, but they are not same. Maybe this is a server and this could be a client, but they talk to each other. And this is a lightweight. What is running here is lightweight in the sense it doesn't need more power, more computing power or memory, or it's a lightweight thing. Kind of, okay, let me give an example of a Skype call on your mobile. The real Skype server, which is feeding all the connections and then feeding the video of from the mobile devices, they also talk. There is a Skype application on your mobile as well as a Skype backend running, but they are not the same level. They are, but they talk to each other in the same way. There will be a presence of everything in the IoT device also. Okay, so have that in mind, because you might think that IoT devices have only the physical layer. No, it's not possible, because there is some level of those other layers need to be there in the present, in those devices. Somewhere it may not be there, all of them may not be there, but don't get confused if you see them also. Okay, so there is an application component running here, and then they feed the data from here. Maybe this application component might know this what is running on this device, may filter out some noisy data from here, and then maybe only pass on the valid data out to the a server which is in the local area network. Okay, this is all, they're all local area network. Imagine this to be a particular industry factory center, operating from different locations. Maybe these are all in different cities. Still, this fog node or server are in the vicinity of these sensors, and this is maybe in a different far off place, could be collecting information from multiple places. So if you imagine all the data which is generated by all these IoT devices need to come here, and a decision has to be taken, and then it has to be passed on to the actuator and the IoT device, you can imagine that time taken for this data to flow up to this point, and the decisions to be taken, and then the results have to come down to the IoT devices for it to behave intelligently. That is the situation when AI algorithm or whatever is running on the cloud. If they are running on the cloud, only on the cloud, and there is no intelligence on any of these places, then all the data, these are all dumb devices, so they all collect the data and pass it and wait for the command. Even if it sees some smoke is detected, it doesn't know whether it has to switch on the engine or something which is getting heated up. They don't know what to do with the data. So that's minimum intelligence have to be there in the edge devices. Now the problem is edge devices will become costly in terms of power and requirement. So the other alternative is to have the intelligence somewhere in the vicinity, which is called fog node. It's called fog computing. If you do all the computation here, it's called edge computing. Edge is anything on the IoT device itself, which is closer to the environment. Whereas if you do it in the middle, it's called fog computing, which is not as powerful as this, because this doesn't have the information about what is happening anywhere else. So that intelligence it doesn't have, but it can take a local decisions. So it is like a state government, and then this is a central government kind of a analogy. Okay, so fog computing is something in between. Okay, you can read this later on. Okay, I don't want to go through it individually, but it's a good pictorial view of what is edge or fog computing. I think you understand the difference now. Let me put it in words. Faster response and real-time insights are two essential things for realizing highly competent and cognitive environment. Remember, cognitive means it takes a decision, smart decisions. That means it should have some AI capabilities to make some decisions. It could be rule-based or neural network-based, which is high-end, but they need to have some intelligence, and highly competent in the sense it should be reliable, and it should work in terms of real-time data which is generated by the IoT devices. And you need a faster response also. So faster response is not possible if you keep all the AI in the cloud. It will be the data has to go up to the cloud and then come back. The decisions have to come back from there. So because of that, edge computing flourished. Okay, they thought that we need to take decisions at the edge itself. Okay, these are the motivation for edge computing to become popular, or only way of doing it. Now there is something in between coming. Fog or edge computing, or I can say fog computing, is leveraging the computing capabilities within a local network. Maybe I will remove this. Okay, now we know the difference between this. So to carry out computation tasks that would ordinarily have been carried out in the cloud. So now what we are doing, instead of doing it in edge, I will do it in the local area network within some device which is powerful enough to perform that job. So to just to give you an analogy, suppose you have a Raspberry Pi, and then which is controlling multiple Arduinos, okay, or small microcontrollers, maybe STM based or ARM Cortex based. So you can say these are all edge computing. You know that Arduino and others are very low power and low efficient, in terms of computing power. Maybe RPA is much powerful because it has a quad core, 4 cores are there in it, and it runs in gigahertz range clock. So we can have fog computing on our RPA and edge computing on these devices. So that's how an analogy is. And through Wi-Fi, this RPI can connect to some router, and then they can communicate. It can communicate back to the cloud. Okay, so that is possible. It can help organizations to reduce their reliance on cloud. So we are removing the reliance on cloud. Even if the internet is down, the service provider has not, it's in maintenance or something has happened, still the devices are intelligent enough to take some local decisions. So they can perform some minimum analyze the data, and then we can remove some latency issues because of keeping the intelligence in the cloud. So we can make decisions, data-driven decisions faster if you have a fog computing. Edge computing usually occurs directly on the devices to which the sensors are attached, or a gateway device that is physically close to the sensor. So if you say gateway, I can call it as a fog computing. If it is happening in the edge devices, it's a edge computing. Okay, I hope it is clear. Normally, more sophisticated algorithms are handled in the cloud, and simpler algorithms are run on the edge devices. Always I told you that what is running on the edges or on the fog is much lower end version of what is running on the cloud. So I hope this is clear so far. Let me see if there are any questions before I proceed further. Okay, only good evening is there. No problem. Let us go. Exactly half an hour. Okay. Okay. Now I am going to talk about two things: having AI in the cloud, having AI in the edge. Okay. Now we understand that when I say edge, it could be fog or edge computing. We will not differentiate now. But I told you that AI has to be there in both the places because of the delay involved, and not possible to have a real-time response or cognitive response to what is happening at the edges. So we need some AI also on the edges, and we need, of course, AI at the cloud for doing some analysis at a over a huge amount of data coming from huge number of devices and places. Okay, so we need the presence of AI in both. So let us see both in a short introduction to them. I want to give you some companies which are involved in this so that you have a broader idea of where you have to apply for after your MTech, or when you get a campus interview, which company to target for. So AI chipset market. See, I told you the most important contributor to the AI is the chipset, the semiconductor industry. Without that, AI will not be there. So that market is growing in terms of billions because of the recent advancements in the AI chipset. NVIDIA and Intel, they are the leaders in this space, but they are challenged by others who are there entering into AI world. They are making chips for AI technologies. Now, when I say chipset for AI, that means the processors which are made for AI has to be programmable. Okay, they need to be programmable, and they should have features in terms of hardware as well as in terms of software libraries, so that AI algorithms can be run on these machines efficiently. You may wonder that why not I use normal CPU, which is maybe Core 7 or whatever. See, these chipsets are all not meant for running AI algorithms. I'll tell you one main reason behind that. You know that this AI data, whichever is coming, let me take our example of IoT. They are all sensor data. Okay, they are not of normally. What happens is based on the range of values that are coming from the devices or sensors, the data type is decided. What data type? Data type means whether to use float 32-bit or a double 64-bit, or should I use, maybe there is a another standard 16-bit floating point standard. Okay, IEEE 754 is the standard for floating point, which I shared with you long time back. It is actually started off with 32-bit and then enhanced to 64-bit, because the range of values that can be represented, decimal numbers, real numbers, are much larger in 64-bit compared to 32. But there is a shorter form of that floating point also, 16-bit. Okay, why do we need such a low-end things? Because the devices which are generating the temperature reading or even pressure reading, they are not going to be having a wider range of data. So you don't need a 64-bit of floating point representation to read this data and send it across. That is one thing. And second reason is, for every reading that you get from the devices, you need to send it across to the cloud or wherever. The bandwidth required for sending a 64-bit data is huge compared to 16-bit data, right? So what happens is, we try to minimize the amount of bits required to represent this data so that the network traffic is not too much, so that we still be efficient enough to collect huge data from the devices at the cloud, okay, or in the network. You can send it across in real time. So not only 16-bit, even 8-bit is considered for IoT devices, because IoT devices themselves are very less power full machines, and they are all very small microcontrollers with 8-bit controller or maybe 16-bit controller. So we cannot even represent huge numbers, and if they need to do it, they need to do longer instructions, which will be power consuming and time consuming. So shorter representation of data always helps you in terms of network traffic, in terms of processing power required, and in terms of time required to process them, manipulate them, and send it across. So that's why the normal CPUs, which are meant for, okay, these CPUs are meant for high-end data, okay, maybe graphics or computer gaming, or for bigger data bit in terms of the valid data available. They are all huge in terms of processing or in terms of generated data. Whereas IoT devices or some of these AI involved things are of smaller dimensions. So we need a different processor to process this kind of data. Okay, that's what I'm driving at. That we cannot use iCore 7, though it is running at 3 gigahertz or range, but they are not meant for processing our AI data. So now coming back, AI chipsets are there. Now there are chipsets for both cloud as well as edges. Public cloud, like these companies having a hosted public cloud which support AI IoT frameworks running on them. So they need chips. Okay, why do they need AI chips? Because they are running a big, huge algorithms, AI algorithms in their cloud. So they need a proper processor so that they can run it faster. So they buy from these chip vendors who are supplying these chips and build systems and hardware, reference hardware, or even the final hardware, and they are good in AI algorithms, and they run it on these chips and take the decision and pass it across to different devices or businesses in the market. So enterprise data centers, which are specific to particular enterprise, private clouds, they are not generic public cloud. And hybrid cloud, which is a combination of both public and private. They are all supported by companies like NetApp. This is HP, okay, enterprise. Now you know that HP is split in, they become HP, Hewlett Packard Enterprise, and Dell, all of you know. So another emerging segment is telco. So telecommunication cloud. They are also maintaining cloud because the network is also getting a lot of data, even their own data, maintenance data, or their user base data. They have also their own data, which is generated in the telecom network. So they need telecom cloud also to process them and then make their system efficient, apart from supporting some other applications using the telecom network. So telecom means I am saying about 3G or 4G or 5G, like Airtel or AT&T, those companies which are providing the telecommunication support or infrastructure. So they also need cloud infrastructure, okay, and they provide. Actually Huawei is one good example where they have they provide the network infrastructure vendors like Huawei. Okay, they make it. Okay, and they use it also. Okay, now one more thing. Maybe I will, while I am talking about chipsets and all that, I'm sure all of you may be aware, but in case you don't know what they are, I'll just briefly talk about what I mean by ASIC. This is application specific integrated circuits. Integrated circuits. There is something called FPGA, field programmable gate arrays. Okay, and then our normal integrated circuits like CPUs, whatever we get, like a ARM core or Intel i Core 7 or Core i7, whatever. Okay. Now, what is this application specific? You know that GPU or CPU, they are programmable. Okay. They are programmable in the sense they are meant for general purpose processors, not meant for a particular application. Okay. Like FPU, you might have seen, you might have heard floating point unit, which is meant for floating point arithmetic, which is part of the CPU. You know GPU, which is meant for general purpose, graphics processing unit, which is for graphics, but still it's programmable. Okay, it's not that specifically for only processing the gaming related video or videos in particular format. They are not meant for a particular JPEG format or MP4 format. It's not meant for a particular format. It can be programmed to process any kind of graphics images coming, and then it can process them. So they are all called general purpose processors and very powerful, but they are meant for general purpose usage. What about ASICs? They are application specific integrated circuits. They are also built like what CPUs are built, the same digital circuits in the same nodes, like nanometer node. You know that 7 nanometer is what is going, and then even below that it is going. The dimensions of the integrated circuits which are made are of this dimensions. Okay, a smaller circuit. If you are drawing a circuit here on a 7 nanometer chip, the width of the line connecting to the network or AND gate or OR gate, they are of width of 7 nanometer or less. Okay, that's what it means by a particular node of a processor. Okay, now what is ASIC? It is a custom made chip made only for a particular application. It could be like, no, I want to make impact 4. Okay, MPEG 4 to be converted into maybe MP4, whatever, some other format, JPEG or whatever, some format I want to Windows format or the BMP format. I want to translate one image format to another image format. I can build one circuit only for that. There is no programmability involved. It expects the data to be available and fed every clock cycle, and it gives you some output which is a BMP format. Okay, I can build something like that. So that is called ASICs. What is the advantage of ASICs? It runs faster as fast as CPU. Okay, but it is meant for a particular application. It's not programmable, so that's a problem, that you cannot change it now later on to convert some other format. So, but people still use this for some specific purposes. Now, I said that CPU and GPU are general purpose. This is general purpose. ASICs is very specific to application. FPGA comes in between. They are programmable in a sense. I can actually program a particular circuit into the FPGA. It's called field programmable gate arrays, where I can program a particular integrated circuit. Okay, I can realize a particular FPGA. I can realize a particular circuit here by programming it, hardware programming. Okay, it's not software programming, though what you are feeding is some data. To program this already built circuits, you interconnect them in the way you want and realize some particular realization of a hardware circuit. So it is programmable in a sense, similar to CPU and GPU. They are programmable, but they are not as efficient as this. The reason being, the hardware is already built, so you cannot be as efficient in terms of hardware circuitry, where the CPUs and GPUs really good in doing it. And similarly, it will not be as faster as the FPUs. Okay, in the sense, for a particular application, whatever you build, it may take a longer route to perform that operation. Okay, But the advantage is it is programmable. So you can buy an FPGA chip. It is like a chip only, but you can program any hardware circuitry inside, and then you can make it work. But sometimes it is not meant for your end product requirements. Okay, it will not be useful for that kind of a thing. But still, people use it. Whereas ASICs are faster and efficient, but they are not programmable. So you can see the differences between these two, all three of them. Okay, so now I give an example so we can go faster. So NVIDIA dominates the AI training in the cloud. Okay, where AI chips are required on the cloud, NVIDIA is dominating there in the market. I will talk about the inferencing and training, though you are aware. Maybe in the next section we can touch upon it. Right now, I'm not going to go into detail. So, whereas inference is more of a free for all, which is not dominated by a single player at present. Right now, which vendor is dominating which area? So, training on the cloud is dominated by NVIDIA, whereas inference area is not dominated by one. There are plenty of companies supplying that chips. Due to inference workload, which differs between verticals. So, what is the inference workload means? The amount of work that is involved in inferencing useful information from data. They differ between verticals. Verticals means different applications. It could be for hospital or health or industry or different domains, different use cases differ in terms of inference, what they need to learn from it. So the current trend is for moving AI inference to edge devices. So what we want to do is AI knowledge, okay, inferencing is done in the edges. Inference is after the training. Okay, training happens with lots of data. You train the neural network, and then once it is trained, the trained neural network is put in the edge devices. Okay, and whatever is actual data is coming here, it is intelligent enough to make a decision. So training is happening in the cloud. Okay, cloud, and inferencing after the training has been done can happen in the edges because it doesn't involve too much of work, computing power for an already trained network to inference some useful information from the data. So that's why we use inferencing engine on the edge devices, because edge devices are always power hungry or power inefficient in terms of they don't have that much of power to run those training networks. So AI applications are difficult to move to the edge, such as whereas some chatbot or conversational AIs cannot move to edges because they need a lot of computing power, which is not available in the edge devices. So, and moreover, these systems will. So, I am just giving you reason why we need AI in the cloud. We cannot do all of them, all the training in the edge devices because they need more power and they are very specific to particular verticals. So we do the training in the cloud and inferencing in the edges. That's what I'm trying to say. Moreover, these systems will evolve from rule-based to the deep learning-based AI, which actually increases the inference workload also. Okay, even inferencing also it's not very easy to do on edge devices unless you have a very efficient hardware to do that. So I'm sure you might have heard about it. A tensor processing unit from Google, and even CPUs and GPUs are used. Intel is coming up with CPUs and NVIDIA's for AI applications. Okay. So how much time we have? Any questions before I go? Oh, already I have come to the end. Okay. Very good. Yeah, you are right. Actually, let me explain. Okay. So I will not continue further. See, ASICs are basically needed for controllers. Okay, controllers. Suppose you take a washing machine example that you brought in. Okay, top loading. Okay, this is not a side loading. Controllers are there. Wheel also is there. Now, this washing machine has so many sensors, like how much of rotation has happened, how much of what is the weight of the cloth you have put in, and how much of water is needed so that they can fill it, and then how much time it has to take, what kind of washing you have chosen. So those things are all processed based on different sensors. And then there is one more thing in washing machine is fuzzy logic. Fuzzy logic means you know that binary logic is 0 or 1, whereas fuzzy logic talks about something in between also. It's not that purely you say that you know some level is 0 1, sorry, 1 or 0. It's not only binary, it could be multiple levels or different level. There is nothing called specific level. That is what is called fuzzy logic. The decisions are not taken based on one particular signal or input. Okay, the magnet, I think in the physics you might have studied about hysteresis, right? When the magnetic field, H and M, B, I don't know whether I am writing it right way. So they have a hysteresis, magnetic. When you are magnetizing some material, they show this kind of a behavior. When they change over from this to this at this area, but when they come back, they come here and do it. So similarly, the fuzzy logic is something which is not specific to area. So that kind of a circuitry is, even logic is put into the washing machine to take a decision when to stop or when to drying has happened or not. Those things are fuzzy logic based in washing machine. So ASICs are used for controllers or different sensors in the washing machine to even implement this kind of fuzzy logic into it. But most of the machines that we have normally now, whatever Samsung or LG they produce, there are lots of controllers also. Programmable controllers are also there, which are required for displaying things on the screen and then choosing the options, those things. So it is ASICs are used for a specific product, a specific circuitry. Okay, meant for a particular as market. Okay, a particular market or a particular product. Whereas microcontrollers or ARM processors or Intel processor, they are all general purpose. Okay, that's the difference between ASICs and normal ICs. Okay. Any other questions, guys, from any one of you while I am taking the attendance? Okay, you may wonder why I am saying all this, going into chip level and all that. You are learning IoT, so when you go into some interviews, the awareness about the where these things are used and how they are used, why you are using algorithms and all the things, if you relate with what is there in the market or what is happening in the real industry, you will be appreciated more. So that's the reason I am talking about all this. So don't think that it is useless or doesn't make any sense for this course. Okay, I'm just trying to tell you the reason behind why I'm talking about all this. Okay, so I think we are only 51. What do you want me to do? Leave you or bore you for some more time? I am asking a tough question. What do you guys want? Want to take a break? Okay, let me see what I want to say. I don't want to run through this. See, actually, I explained a lot about this. I don't mind finishing it if you don't mind also. So let me tell you what I meant by AI in Edge. Okay, it's a related topic, so let us finish it. Not much. You don't have to remember any of this, but it's a huge billion market. And I told you that Edge AI inference chipset market. Okay. I told you inference happens in edges and training happens in cloud. So Edge AI inference chipsets market is what is around this much right now, 2018. Okay, it may be much more. They expect to grow to this level. Okay, in 2026. What is Edge AI? Robotics is a good example. Okay, wherein different kinds of neural networks have to run on robots. Like, I am not going to details of any of them. Now SLAM for navigation, simultaneous location and mapping. If the robot has to move into the particular environment, conversational API for machine interface. I have seen in shop when I was working in shop, a robotic vacuum cleaner talks to the owner. You can talk to that. It will ask you a question. How are you? How was the day and all that. So It was there way back in 2014 or somewhere when I was in Sharp. So conversational AI was there during that time, on robotics vacuum cleaner. Okay, machine vision for object detection, that. So there are different algorithms for each, and robots needs all of them running on the edge devices. You can imagine how much of complexity there in it. So both CPUs and ASICs based GPUs or solutions are there. They are the companies. The second niche market is industrial applications, both in manufacturing and smart building and oil and natural gas. So FPGA, I explained to you, they are required for supporting legacy equipments. Okay, don't have to know everything. I'm just giving you a broad picture of why AI is required and what is involved in having AI on the edges. That's all. Okay, so that's about this. So Xilinx and Altera are, they're all very good companies. Xilinx is where FPGA was invented, and they are FPGA vendors. Okay. Now, one more thing before I stop. AI can be on very edge. Very edge means it's at the device level, at the not even a fog computing. It is like a small micro sensors having AI knowledge built into it. Okay, they are called very edge, and normally they are made of FPGA companies. And RISC-V, I mentioned it yesterday. This is the synonym for Linux in the software world. This is a open source hardware design of reduced instruction set computing. Google about it. It's very, very good. You should know about this as you are coming out of into the industry. Due to the larger shipment volume, smartphones are actually taking a lead in terms of AI chip market. Okay, and you know that Qualcomm, Samsung, and HiSilicon and RISC-V are tied up, and Apple. They are all good companies having these products. Software is crucial in these implementations on the edge. So whatever software we write for edge AI chipset, they run on them. Okay, inference engine or whatever we run, they need to run on those edge devices. So even NVIDIA, what they have done is similar to RISC-V, which is open source. NVIDIA is opening up the development of different algorithms using their GPUs to the developer community. Like Linux is open to everybody. Even NVIDIA is doing so that their GPUs are becoming popular and more people will be using their GPUs on different applications. So that is a motive for this. Okay, like Intel and Xilinx. Xilinx is a FPGA vendor. Okay, just for your knowledge. Okay, I think I successfully done. I hope you understood. I will not go beyond it because I don't have anything to do. Talk. Thank you, guys.